Welcome. In modern deep learning, the attention mechanism has absolutely revolutionized how models process sequential data. Before attention, recurrent neural networks struggled significantly with long-range dependencies, forcing entire input sequences to be compressed into a single, fixed-size context vector. Attention fundamentally solves this information bottleneck by allowing models to dynamically focus on the most relevant parts of the input sequence. The core mathematical concept relies on an information retrieval analogy utilizing queries, keys, and values. Imagine querying a large database. You issue a query representing exactly what you are looking for. The database compares your query against the keys of all available records. The computed similarities between the query and the keys determine precisely how much of each corresponding value is retrieved. In neural network architectures, we generate these queries, keys, and values through learned linear transformations. Given an input sequence matrix X, we independently multiply it by three distinct weight matrices, WQ, WK, and WV. This operation projects our original sequence embeddings into three entirely separate representation spaces, yielding the highly specialized matrices Q, K, and V used specifically for attention. To intuitively determine which items in our sequence should attend to one another, we must compute a similarity score. We achieve this by taking the mathematical dot product of the query matrix with the transposed key matrix. The result is a square matrix of raw, unnormalized attention scores, directly representing the alignment and relevance between every individual query and key pair. However, as the hidden model dimension, formerly denoted as dk, grows larger, these raw dot products can become exceptionally enormous in magnitude. This dramatically pushes the subsequent softmax function into regions with extremely small gradients, severely exacerbating the vanishing gradient problem. To counteract this instability, we scale the raw dot products down by dividing them by the square root of dk. Next, we apply the standard softmax function row-wise to these scaled similarity scores. The softmax operation mathematically normalizes the raw scores so that they are strictly positive and sum to exactly 1 for each query. These normalized values effectively act as the attention weights, representing a discrete probability distribution. They explicitly instruct the neural network on exactly where to focus its attention. Finally, we multiply these computed attention weights by the corresponding value matrix, V. This critical step aggregates the values based entirely on the learned weights. Sequence elements with high attention scores contribute heavily to the final output representation, while completely irrelevant elements are heavily suppressed. This provides the complete scaled dot product attention formula, the foundational engine driving modern transformer architectures. When the queries, keys, and values all logically originate from the exact same source sequence, this specific operation is referred to as self-attention. It allows a sequence to continuously build a rich internal representation by mathematically relating every single element to every other element. In a transformer encoder block, self-attention helps a word gather semantic context from all surrounding words perfectly. In stark contrast, cross-attention deliberately blends information from two distinctly different sequences. Typically utilized in decoder architectures, the queries are mathematically derived from the decoder's current internal state, while the keys and values are sourced directly from the final encoder's outputs. This crucial architectural difference allows generative models to perfectly align their target outputs with the original source input data. A single attention mechanism inherently has a critical limitation. It can fundamentally only focus on one specific subspace of feature similarities at a time. To capture multiple complex relationships such as syntax, semantics, and grammatical structure simultaneously, we employ multi-head attention. We systematically partition the embedding dimension into multiple independent heads, each simultaneously computing its own projected scaled dot product attention. Each independent attention head performs scaled dot product attention entirely in parallel, successfully extracting vastly different contextual features. The resulting value matrices from all these independent heads are then sequentially concatenated together into a single, wide matrix representation. Finally, a learned linear transformation is seamlessly applied to this concatenated result, mapping it efficiently back to the model's original sequence hidden dimension. In summary, the attention mechanism fundamentally replaces rigid, sequential architectural bottlenecks with highly dynamic, massively parallelized context gathering. By effectively leveraging queries, keys, and values, carefully scaling the dot products to preserve stable gradients, and systematically splitting workloads across multiple attention heads, attention enables deep learning models to capture highly complex, long-range dependencies across arbitrary data sequences seamlessly.